Woohoo! Welcome back. Today we're going to be talking about finding the slope at the tangent line with our friend Ryan Kellogg of the Savannah Bananas. Yay! And we picked Ryan Kellogg today because he can actually throw a baseball about 40 meters per second. Yay! So we're going to ask him to be throwing rocks for us so we can do math, and I'm sure he'd love to help. So we're going to have Ryan throw a rock, and it's going to go upward with a velocity of 40 meters per second. And we're going to get a formula for height that is in meters, and t seconds later, it will be given by 40t minus 9.8t squared plus 2. So the 40 comes from the initial velocity. The 9.8 meters per second squared, that's the pull of gravity. So gravity is pulling back down. And then plus 2, well, this is an estimate, but I'm guessing that his hand is up about 2 meters above the ground. Now keep in mind, in this picture, he's actually pitching horizontally, but we're imagining he's going to throw the baseball up in the air. So that's the situation we have here. And through the magic of television, I've got a graph that describes this motion where the y-axis is actually the height and the x-axis is now t, time in seconds. The height is in meters and the time is in seconds. Woohoo! And the question we have is, what is the slope of the line it would travel after t equals 1 second if gravity suddenly turned off? Ooh, so in other words, Ryan Kellogg is floating off into space. Goodbye, Ryan. Okay, and that gives us lots of room to draw a picture. So if gravity suddenly turned off right at t equals 1 second on the graph, that's that spot right there, then we would expect that this rock or baseball would head off along what's called the tangent line. Now, tangents are very hard to draw, so I did a good estimate, but as always, this is not exact. You're going to want to turn to a computer program to get a really beautiful version of this. Or wait until later when you learn more calculus, and then we can use calculus to do this. So this is what we're expecting would happen after 1 second. Instead of curving upward and then being pulled back down by gravity, if gravity suddenly shut off, then the rock would go flying off along a straight line. And so what we want to know is, what is the slope of this line? Okay, so that's pretty cool. We want to figure out what that line is, just in case, gravity could shut off any moment now. We don't know. And so, through the magic of television, I have a chart of values. Because I picked a particularly gruesome height function, I decided to go with one that was correct instead of one that was, nice numbers, but, nicer to work with. So we've got some kind of gruesome data points. But basically what I did was I took our formula from over here and I calculated all the values of the height. So remember, again, these are in meters and t is in seconds. And so at 0, the height of the rock is 2 meters because Ryan Kellogg is still holding it. Then, as time moves forward, the height gets higher and higher. Now, if we look at this graph, right around 2 seconds, the ball would start to fall back again. It would reach its maximum height just a little bit beyond 2. So a little bit after 2 seconds, it would stop and then head back down. We're not worried about that because we're looking right here. And so I calculated where it would be at 1.5 seconds, but then I decided to do something interesting. I decided to look at some other values that are between 1 and 1.5, just for funsies. So I calculated these, and these are all the heights. And as you can see, 1.5 of all of these values, 1.5 seconds is going to give us the highest value in the height of all of these. And then 1.2, 1, 2, 3, 4. So here's 1.1, here's 1.2, and all the other points are going to be in between 1 and 1.1. So the next question is, how do I find the slope using these values? Well, first thing we're going to need is the slope formula. Ooh, ah, ooh. And we've got that lovely slope formula. That is the slope formula we're used to. The slope is the rise over the run, which is the change in y, or output, over the change in x, or input. Now, in our case, this is going to be t, time, and I did use y's. The one problem with this, as I've written out here, is that this formula requires two different points. And the question asked, what happens at this one point? And so here's where the rest of the chart is going to get useful. I can't come up with a slope at a single point. That's not going to be something I can use this formula for. So what I'm going to do instead is I'm going to try calculating the slope between the point 1, which up here you see the height is 32.2 meters, and let's say 1.5. 1.5 would give us 39.95 meters. Let's look at what's happening on the graph. If I look at the slope between 1 and 1.5, I get that line. Ooh, isn't that fancy? Got a little black on the highlighter, so that makes it very fancy. So do you see how this is not quite right? It's not quite right, but it's really close. And so when I calculate that, and I used these values, so I used these two values right here, 32.2 and 39.95. Those are the two y values. And I used these 2 points right here, 1 and 1.5. And I did the subtraction and I canceled, and it's 15.5. And I happen to know that the slope of position is velocity. So it tells me it's going 15.5 meters per second. That's our slope. So that's interesting. But is that the correct value? And the answer is, well, it's close. It's not quite right. And so what I'm going to do is I'm going to calculate a bunch of other slopes. So what does that mean? Well, again, through the magic of television, so you guys don't have to watch me use my calculator and try to calculate all these things. I have gone ahead and prepared a bunch of points between 1 and 1.5, between 1 and 1.2, between 1 and 1.1, between 1 and 1.01, and so on and so forth. And each time I have calculated that slope. Now, what is going on here in the graph? Well, what's happening is I'm starting here between 1 and 1.5. Pretty close to the line I was looking for, but a little bit off. And if what I do is I move this value, I move closer and closer to 1, what's going to happen to the slope? Well, if I pinch this at t equals 1, right there, t equals 1, and then I move the second point closer as so like here's 1.2, here's 1.1. I can't draw in all the others, but as they get closer and closer to t equals 1, what's going to happen when I draw the line that sits between them? It's going to get closer and closer until eventually we'll be right next to the line we're looking for. And so let's take a look at what happens with the data. So over here, if I start out between 1 and 1.5, as I showed you, I had 15.5. Then between 1 and 1.2, it's 18.44. 1 and 1.1, 19.42. 1 and 1.01. Oh, don't look at that yet. 1 and 1.01, it's 20.302. 1 and 1.001. So I'm getting really, really close. 20.3902. 1 and 1.0001. 20.399. And as the second points get closer and closer to t equals 1, what's happening here? The slope gets closer and closer to, what do you think? And we'd have to guess. Now, if we're not even sure, if we're looking at this going, it's not really clear, what's the next point we could look at? Well, we could look at what happens between 1.32.2 and, well, I'd follow the same pattern and just put in 4 zeros, figure out what that y value was, and get the new slope. So you can keep going. You can go for as long as you need to until you see the pattern, but it seems to me like it's getting closer and closer to 20.39 or 20.4 or something. And what I can tell you through the magic of calculus is that, in fact, the slope of the tangent line at t equals 1 is 20.4. And that's something we'll be able to confirm later on with calculus. So you just have to take my word for it right now. But this is how we're going to get there right now. And if you don't see the pattern, keep going. More data points. Just make your tables really, really long until you see what the pattern is and you can make an educated guess. So, woohoo! You guys are awesome. You made it through the video. Yay! Woohoo! And look, we turned gravity back on. So Ryan Kellogg comes back to Earth. Yay! Having seen the universe. Woohoo! Singing Drops of Jupiter. Maybe that's too old. Ignore me. Okay. Woo. And I hope you guys have a really wonderful day, night, afternoon, whatever time of day it is. I hope you're having an awesome time. And remember to woohoo and math on. Take care. Woohoo!